So you guys have been hearing about UI development, maybe since morning in some way or the other. Because when you talk about things like machine learning, you talk about actions on Google. What you're ultimately doing is presenting content on the screen, right? And you guys interact with your phone, screens, or all kinds. But what you see ultimately is an interface, the user interface. So what I want to talk to you today is give you a perspective of how to approach UI development, and also take my collective experience of more than 15 years and kind of condense it down to a set of things that you need to do as a UI developer when you're starting to build your applications. All right? So this talk is going to be called Thinking in UI, which is a way of building a mindset or conditioning your mind to think in terms of how do you go about taking a design, a nice-looking design, and convert it to a working application, be it Android or Flutter or React, or whatever framework you choose to use. And hopefully it'll light a few bulbs in your head about how to go about doing this. All right? So UI development actually is not just about computer science. It's not about just simply building something and showing it on the screen. It actually is a confluence of several different fields which come together on the screen for you. And these are just a few of them. After all, if you consider things like errors, they are represented by red color. Anyone can tell me why red has been chosen as a color to represent errors or anything bad? Danger, I hear one. Can be seen from far. High energy, very warm, yeah, intense color. So, yes, now we're getting into the physics aspect of it. But the idea is that this color apparently is genetically wired into our heads. Because the color of blood is red, right? And if you consider the evolutionary instincts that we have developed over the last millions of years, we basically run from predators. People who want to eat us and let the blood spill out, right? So escaping is a way of telling you that, this is not something good, or stay away from it. So red has been used very nicely in UIs and all kinds of places to indicate danger or telling you something that is bad or wrong, right? So that's coming from anthropology, computer science, psychology, and all of those areas. So UI, as you can see now, it's actually not just about building things on the screen. It's actually collective wisdom that has come over several decades of millions of years. Now, when you want to approach UI development, you actually have to break down the process. It's not just you take something which is seeing on a screen, it's in the form of some design, and immediately translating it to some framework or technology. The translation doesn't happen immediately, right? There is a process in between. And what I want to give to you today is that process and break it down into a set of steps that you can apply to your own projects. Now, how many of you have actually done UI development in the past? Build any kind of application, presented any kind of screen, right? Enough of us over here. So you know the process. There is something to it. But sometimes it may seem a little mysterious. Like how do you go about actually taking this design and converting it to something which will look nice on the screen? So there are actually 4 steps of doing this. And these are the 4 steps you can see over here. And we'll take each one of them one by one. So let's start with decomposition. Now, normally when you're building an application, you have some design in your head, right? You're probably scribbling something on the paper, or you're designing something with a tool, but ultimately you have a notion of what you want to present onto the screen. And that's the role of a UX person. Normally, if you have a larger team, you will have somebody designated as a UX person who will actually go about designing these things. And their job is to think in terms of fancy graphics, putting nice rectangles and colors on the screen, and creating animation, sound, motion design, all of those kinds of things. And you as a developer who is supposed to finally translate these things into something meaningful and useful to the user, they have to do this translation where, okay, I take this fancy design, but how do I actually build it in the framework of my choice, right? And I can use any of the frameworks that we have been seeing since morning, And in fact, you'll be seeing one more talk where you can talk about Android being one of the application platforms that we can use to build these UIs. So you are doing this task of translation where you're seeing a design and mentally doing something in your head to see how we can be translated into something useful on the screen. And you're thinking in terms of these components. You're breaking down the design, and you're saying, oh, you know what? This actually is a set of layers which need to be combined together. And you're doing this translation all the time. But there is this gap in between, right? The UX is presenting you something, and you are thinking something else. And that gap needs to be broken down in some way or the other. So if you take this design, for example, it's not just a flattened graphic. Ultimately, what you're really going to want to do is take a set of layers, a set of components, and then finally flatten them out and present it onto the screen. And this requires creating a hierarchy. Any of you has created applications using Android? Written HTML? How many of you have written HTML? Right? Most of you, right? So what does HTML look like? It's essentially a set of XML tags, right? Each of those tags is actually a set of components. And you can compose tags within each other and create a hierarchy of components. And that's what HTML is all about ultimately. And you take this hierarchy and then flatten it out on the screen, and you get your components are the final UI. Let's take a different example, for example. So here if you take a watch like this, it looks fancy, right? There's a lot of design elements going around in this. You see the strap, the dials, and a bunch of numbers on the screen, and all kinds of stuff. But you as a developer needs to break it down. You have to take this design and break it down into a bunch of components. And these components you'll be building using HTML tags. It could be components on a UI platform, which are again then flattened together to eventually build the UI onto the screen. This is how you're going to do your component-driven development. And this whole thing comes down to that, In fact, this particular way of thinking about user interfaces has been made very popular in the past 5 years or so. If you take frameworks like Angular, React, Flutter, which has come out from Google very recently, Android development, or any other platform that you see in the past as well, this is an idea and a principle that is applied to all the UI platforms that we have today. And this is just a few examples where you see this applied. And when you as a developer go out into the market and start learning these application platforms, you will see that this particular idea becomes very, very useful. You start training your mind to think in terms of decomposing a design into a set of components. But there's a lot more to it than just decomposing into components. In fact, what you're doing as a user interface developer or an application developer is take some aspect of your domain, which is consisting of all these different kinds of jargon, You have your entities, relationships, operations, etc., etc. That example that we saw earlier where you're spinning a wheel and you're selecting a name, there's a bunch of things going on over there, right? It's working in a particular domain of having a set of names. The names are represented radially, and then you have a spinning wheel which is stopping at some point after the momentum comes to 0 maybe, and then you're picking the name that fits the pointer, right? And there is a design to it. There's a certain jargon that you use to describe that particular application. And jargon, I mean the language you use to describe it. Spinning wheel, stopping, rotating, radial lines, and so on and so forth. And that's what you use to describe the domain. But you as an application developer has to translate this domain into a set of working user interface elements. So you take the UI, and you have a totally different jargon over there. The language you use over there is like graphics, design, interactions, animations, events, and so on and so forth. Right? So you have two different worlds over here. There is the domain world, where you're talking about the requirements that you get from your person or someone from your team, and you're translating that into your working application. So you have to cross this bridge over here, where you're taking the requirements or the language of the domain and translating it to a user interface metaphors, which is mostly all these components, application, animations, and so on. So traversing this bridge is what you do as an application developer also. And there are a lot of different techniques you can use from a development perspective. And some of them are simply listed over here, which is domain-driven design. If you haven't heard of this particular term, I urge you and encourage you to take a look at this book called Domain-Driven Design by Eric Evans. It was written back in 2003, and it was primarily meant for back-end developers who are building like middle tiers and back-end systems. But this particular book is so relevant for even front-end developers. And there's no need for you to actually, when you look at the book, you feel intimidated. You know what? This book looks big. Maybe I can use it as a monitor stand instead of actually reading it. Or maybe I can put it on my pillow and raise the level of my pillow, maybe. But do take some time to read it. In fact, I myself has taken probably 2 to 3 years to fully understand this book. So this is not an easy book to read. But once you read it, you realize that there's so much knowledge and wisdom in it, you will be set for the rest of your professional career in this particular field. In addition to that, you also have functional programming, object-oriented programming. Many of you who are in the second year, third year, like I see second year, third year students who raised hands last, right? How many of you are in the second and third year? Majority of you, actually. So some of you must already be learning about this stuff, right? Object-oriented programming, maybe with languages like Java, C++, Python, and functional programming, right? Thinking with closures, currying, partial application. Like, these terms may seem very archaic, but do get into this, because that's the way you represent your UIs on the screen. And of course, component-oriented development. Now, if you take the responsibilities of a UI, and I'm going through this very quickly because I want to give you a full coverage of the landscape as to how you go about thinking as a UI developer. So if you take a UI on the screen, it is broken down into a set of layers. At the bottommost layer, you have a set of rectangles. Ultimately, you have a rectangular screen on this, that you want to look at, right? You want to break it down into a bunch of smaller areas. That's what you do with the layout. Inside the layout, you create a set of rectangles, And then within those rectangles, you paint different controls, components, and so on. And then you have interactions because the user ultimately has to interact with these components. And animations, behaviors, all of these things are layered on top of it. And when they flatten together, you get the final UI. In addition to that, you also have to think about something called a state analysis. It's basically a way of knowing what are the possible ways states a UI can be in. Right? You can start with an empty inbox. Right? If you have an email application, imagine the case where you have no emails. You're signed up for a new email service for the first time ever, so obviously you may not have received any emails. So what does that state look like? And what happens when you have some emails? What happens when you have selected an email? What happens when you swipe on one of the emails? You have to see gestures for them, right? So these are all the different states in which a UI can be when you're interacting with the application. So this state analysis is also equally important, and you will do it as part of your design. Even if you don't actually put it down on paper, when you start building the application, you will see that you'll be doing these things manually or implicitly. Now, in addition to that, a lot of additional states you have to worry about as a mobile developer, or if you're building for the web as well. So you have to worry about all these additional conditions, right? Is my app authenticated? Is the user already logged in? Have I received a notification? Am I offline or online? And what's the size of the screen I'm looking at? Am I in landscape mode or portrait mode? All of those additional details are equally important when you're designing for your user interface. Because a user can be of any kind and every kind, actually. In fact, there'll be users who could even be animals. So that's all about decomposition. It's a way of breaking down your designs into a set of usable components and then piecing them together to create the final interface. So let's talk about structure. So what is structure? So I want to summarize structure in a very simple way. If you look at your application, this is what you will see from a really top level. You have your app at the top, right? This is the single most thing that you're building. And the app contains a set of features. Ultimately, you describe your application in a set of features, right? When you go to buy a new car or a new motorbike, what do you ask the dealer? What are the features, right? How fast does it go? Does it have a digital dashboard? How often do I need to fill my petrol? How big is the tank? Those are all the features you ask for. And that's all you need to ask for of your application also. So when you want to divide your application into a bunch of implementation sections or functional areas, the features are what are prominent over there. So divide it into a bunch of features, and the features can be built up of several screens or pages. If you're building a web app, maybe it has a set of pages. If you have a single application on your mobile device, maybe it's a set of screens. And each of those screens are built by components. Components are built out of other components. They have a whole hierarchy over there. And they can also be controls which you are actually interacting with, like a form component which has a bunch of input controls in it. That's the high-level view of what an application looks like from a distance. Now, to actually start working on the application, you need to start giving it some structure, a way of defining how this app needs to be built as a team. And this is where this principle of SIC comes in. It's a SIC principle. Not SIC in the terms of being really bad, but SIC, which stands for structure, isolation, and composition. So what does structure actually mean? It basically means how do you place your files and folders on your file system, right? If you want to define your application as a set of features, you have to create folders for each of those features, and then have the implementation files on each of those feature folders. And features could be more complex. You could have features within features, and so on and so forth. You can place them inside each other. So when someone who new joins to your team, they can actually look at your application folder and tell immediately, okay, what this application seems to be doing all of these different things, and this is how the application is built up. You're not going to see views, models, controllers, and all technical jargon that you want to use in your framework. Never ever do that, because then you're confusing a user. Every application starts looking like that. If you're building an Angular app or an Android app or a React app, you start putting view, model, controllers in those places. And that's when you start losing the onboarding audience. They start realizing that every app looks the same, so how is it different? So don't do that. Always think in terms of features. And now once you're done that, you can isolate the single component, because ultimately your UI is a collection of components, a hierarchy of components, right? So every component will have some inputs, some outputs, and a component can also have events that you actually place or interact with. And finally, when you have components which are completely isolated from each other, you can compose them together to actually build up the tree. So your UI is ultimately a composition of all of these individual components, where the data is flowing through each of those components. And what kind of data would you deal with? So your data is of different kinds, but they always come in these shapes. You have the singular data, you have the list, and you have the hierarchy, and then you have the composite. These are the only types in which you will see data manifesting on your screen. Irrespective of how complex the domain looks like, these are the only possible shapes in which you will see your data. Singular elements, a list of elements, hierarchy, or composites. That's it. And if you think of it, all of your UI controls are built around these shapes. Right? You have a list control for a list. A singular control for a single element, like an input control is for a singular text element. And hierarchy is like a tree view. Right? So your shape of data kind of manifests very nicely on the UI side as well. So that's structure. Next, I want to get into communication. Like how do you go about communicating between different parts of your application? And there's a standard mantra that we use when we talk about application is that data always flows down. If you think of your application, you don't receive data from the bottom. Your form control doesn't get the data. The data always comes from the top, probably making a server request, you're getting the JSON, and then the JSON is being spread across your entire application. Right? So data always flows down. And in these frameworks that have come in the past few years, there is this notion of a unidirectional data flow, which always means that data always flows in one direction. Always from top to bottom, top to bottom. So data down, remember this, and never violate it. Never send your data back up. If you want to send something back up, you have to use something else, which is events. So events is how you communicate from any part of your tree to every other part of the tree. So data always flows down, which is what you receive from the outside. And when you want to talk about interactions happening within your application, you have to use events which surface up back to the top of the tree. And these events are what you use to finally send something back to the server. So data down, events up is like a mantra that you need to apply across your application. Never violate that flow. Now, one other thing you will see very common in UI application is this notion of a UI being a function of state. And I'm giving you all kinds of different ideas, but just get the exposure to all these different terms, because when you start building your applications, you'll be encountering this in some form or the other on internet blogs, videos, and so on and so forth. So this function is actually, this equation actually is very fundamental to UI development. What you're really doing is that you're taking data, applying a transformative function on it, and then you get back UI. It almost looks like the equation that Ajinkya talked about, from the machine learning thing, right? You have some input, and you have some output, and someone sits in between who is the function. So here you have a very similar kind of an equation. So the input is your data, output is the UI, and this function does a transformation for you. So remember this equation and make sure that given any state, you always get back the same UI. Right? That's the rule of mathematics, right? Given the same inputs, you get back the same outputs. When I add 2 plus 2, I get back 4 the first time. When I add it again, do I get back 5? Right? It doesn't change. The output doesn't change. So make sure your UI also doesn't change if the state is the same. So that's about communication. Now I want to get into a different side of UI development, which is the science. And the science is actually what you guys will be learning as part of your engineering courses maybe. And tell me if you're not learning it, then maybe you have to find some information outside, or come to me maybe. So what is the science behind UI? Ultimately, everything is built up of software, right? What you see on the screen is just a set of softwares. But there's one notion that has been quite actually staggering to hear, is that all UI run on a single thread. Did you guys know that? UIs always work on a single thread. Even though we're living in a multi-core age, where you can have like 16 cores, 24 cores, or even more than that, But a UI always runs on a single thread. And the reason for that is that the painting of things on the screen and the way the user interacts with it has to be done in a sequenced fashion. When I'm interacting with the UI and painting something on the screen, I don't want to disrupt the flow. Right? So there has to be an ordered sequence in which things have to be done. And to maintain that order, you need a single thread. Because threads always work in one direction. Right? You start the instruction and go on till the last instruction. And somewhere in between, you have to stop. If you have a single thread, it will start with the first instruction, stop with the last instruction. So how do you make sure you stop the thread in between and make sure it never exits? Can you guys think of a way of making a thread never exit? Loops. Yes, loops. But just a loop that executes only one time, or? Exactly, an infinite loop. So now you guys proved yourself that you are actually in computer science world. Infinite loops is how you keep a single thread running forever. And that's exactly how we do it with event loops. There's this notion of an event loop that's running inside your UI application that's constantly spinning. And it's actually reading a message from something called as a queue or a message queue. And every time a message comes in, It actually reads one at a time, processes it, and then goes on to the next message. And it keeps doing it until it reaches the last message. And one of the last messages it will reach could be, what could be the last message for a UI application? Terminate, exit from the application, right? Or in case of mobile application, you just swipe or maybe not use it at all, right? So you can go in the background, foreground, or something of that sort. So an event loop is what is maintaining this set of messages, and it's draining the queue one message at a time. And what's important over here is that processing a message has to be done quickly, very quickly, in fact. In fact, it has to be done at 60 frames per second. Do you guys know why 60 frames per second? We keep hearing this term again and again. 60 frames per second. That's the refresh rate of your display, right? Your current hardware are actually running at 60 frames per second. So in order to get a buttery, smooth UI experience, your software has to be in sync with the display rate of your hardware. So the scan beam that goes along are the LED screens which are lighting up the phosphors inside your screen. They have to be running at 60 frames per second. So if your UI is actually running slower than that, it will seem like something is not happening right. Imagine playing a game where the frame rate is very low, right? You are moving, but the character is taking like probably 3 seconds to move this way, right? That's a very bad experience. And to avoid that, you have to run at the rate of the hardware, which is 60 frames per second. That's because the current hardware that we are dealing with is 60 frames per second. When you get into the world of VR, virtual reality, augmented reality, or the headsets that you wear down, these headsets actually run at 120 frames per second, 90 to 120 frames per second. The frequency is much higher because when you are moving your head quickly, the frequency of refresh has to be much higher. 60 frames per second actually is not enough. It feels very laggy, right? So when you're processing things at that high rate, your message processing inside the event loop has to be also done at the same rate. And then that basically boils down to 16 milliseconds per frame or per message, right? That's the amount of time you have to process a message. Now let's see what kind of messages you can actually put in this queue. There's the callbacks. When you click on a button, a callback is fired, right? And that callback needs to be executing in 16 milliseconds. Have you guys done callback event-based programming? Right? You cause an event, and the event actually executes some function which has to be executed quickly enough. If you don't execute in 16 milliseconds, or let's say you run a while loop inside that, your UI could just freeze or hang, right? Nothing is happening. You're scrolling, you're clicking, but nothing's happening. Imagine the case of most bank websites these days, right? You click on submit. You don't know whether it actually has done the job or not. Sometimes it can take really long time to actually know. And then you say submit multiple times, so you have sent like money 10 times maybe to the user. You don't know, you never know what happens, right? Maybe your statement will tell you finally what will happen. But that could happen too. So it's how you design these interfaces. If your events are taking longer to process, the UI can slow down actually, drastically sometimes. Now a different aspect of computer science that is applied in this world of UI development is rendering. Because ultimately painting things on the screen is what's important. If you don't see any output on the screen, it almost feels like the UI is dead. There is nothing happening on the screen. But there is a caution over here, right? When you talk about things like actions on Google or voice-based interfaces, you don't have an interface to start with. There's nothing visual, right? The whole idea over there is very different. But here we're talking about graphical interfaces, which actually have a screen output. So you have some visuals and graphics to paint on it. And it turns out there are only two possible ways in which you can paint on the screen. There's one called the retained mode, which basically looks like a hierarchy of nodes. And in this, basically the reason why it's called retained is because the whole hierarchy is maintained in memory. It is retained in memory. So there's actually an object model that is used to actually paint things on the screen. So when you receive an event at, let's say, one of these elements, these events can actually bubble up. Because you now have a hierarchy of components, the notion of bubbling comes up in events. And similarly, events can actually also come from the top down. So when you receive an event at the bottom, it can actually go down, and you have a way of even trapping these events. So the whole idea of having a hierarchy in between and retaining a model in memory allows you to do these kind of things. So it's easy to process events. You know which rectangle you clicked. You know what element you actually controlled on, or whatever you swiped on, you actually know what element the swipe happened on. So the whole idea of retained mode interfaces allows you to build these interfaces much more easily. But on the other hand, you have these immediate mode interfaces, which are rendered immediately onto the screen, and they are rendered frame by frame. So it actually literally paints things one at a time. And every time it paints something, it scratches off everything and paints the whole world again. In fact, can you guys give me an example where we use retain mode and immediate mode. I know I'm giving you some examples over here, but I want to name some applications maybe where you see the immediate mode being used very powerfully. Games. Classic example. In a game, every frame is painted, frame by frame, right? And we use powerful hardware like GPUs to paint these things. And because GPUs can process things in a multi-threaded fashion, you can actually paint per pixel, send it out to all the cores on your GPU, and get the complete image in a quick shot. So the whole display pipeline is what I want to touch upon next, which is how we actually get graphics, or the pixels, onto the screen. This whole idea of layout, to painting, to compositing, that's a three-stage process to get something onto the screen. The first step is to, given the rectangular screen, to carve out a space where you want to actually paint. And that's what layout does. It's a process of identifying the rectangles on the screen with a certain width and height and certain location within which you want to actually do the painting. And painting is the process of actually filling it with pixels, where you can have the backgrounds, the borders, colors, etc., etc. And finally, you have to send this image to a hardware, which in most cases these days is the GPU. And the GPU is where you can do some fancy things like applying opacities, animations, blend modes, and so on and so forth. And this whole pipeline runs frame by frame. And the retain mode approach to actually building UIs allows you to actually skip some steps in between. You don't have to do this layout, painting, compositing every single time. Let's say you want to actually just dim the opacity of an element, you can do it directly on the GPU. There's no need to go through the whole layout painting process, which happens on the CPU actually. Right? So this way you can actually improve the performance of your application as well. So these are the things which actually talk about the science behind the UI. And together, we have these four things that you have to do as an application developer when you're building your apps. You start by decomposing the designs that you receive from your application, from your UX folks, right? That's the first step that you do. Once you decompose the designs, you have a way of structuring your application, because ultimately you have to place things in the right folders, because you want to scale an application over time, you want to work with a team, you want to actually put things in the right place, define the components, their inputs and outputs, and compose the whole application tree, and then establish communication between them. Data down, events up, right? And then finally, when you communicate between all of these things, you get back your UI on your screen by going through the process of the display pipeline. And these are all the things which actually come together when you think about your UI.